All right, so for starting this one, we are looking for the equation of the tangent line, which instantly should make me think of derivative, because derivative, of course, means slope of the tangent line. So first thing we got to do then, find the derivative here. So we're going to figure out what y prime equals. And so derivative of 3x, of course, is just 3. And then we go into the plus. So notice, some people end up seeing that plus there and they associate it with product rule, but we don't need any special rule here. The plus gets put in at the end when using product rule. It shouldn't be there in the start. Because when we were just adding terms, we find the derivative of each term individually. So now we do the derivative of 6 cosine of x, which is going to be 6 times a negative sine of x. Now, of course, we could clean this up a little bit, and we might as well, since we're going to be working with this a little bit more. So then we have 3 minus 6 sine of x. All right, now we have our derivative. What do I do next with that information to start getting to the equation of the tangent? Yeah, plug in. Specifically, we're plugging our point into this equation. And again, notice it's y prime, not y, so I cannot plug this y in. All I can plug in then is the x. So I'm going to take that x value and plug it in for x, then see what that equals. Yes, you need to know the unit circle value for this. All right, so we got to figure out now what is the sine of pi over 3. Be able to visualize your unit circle. So of course 0 is going over here. Pi over 3, that's the bigger angle over here. It's the equivalent of 60 degrees if you're helping kind of visualize exactly what we're talking about. I'll accentuate the fact that it is a little bit bigger there. All right, so then we're looking for the sine value. Sine, of course, is the y coordinate. That's how far we're going up. That's the bigger of the two. So between root 3 over 2 and 1/2, it's the bigger one, so that's the root 3 over 2. So that is our actual sine value that we should know there. And if you don't know it, get to know it. You're going to find that these values keep coming back. And yes, you're going to need to be able to come up with all these different sine and cosine values. You're going to need to know your unit circle trigonometry in order to be successful in calculus. And not just this calculus class, but the next calculus classes that follow as well. All right, once we're here, we can go ahead and finish figuring out what our slope is. So we're going to be doing 3 minus, go ahead and clean that up. That would be 3 root 3. And that's basically as simple as we can make it. This stuff was given in exact terms, so I want to give that answer in exact terms as well. So now we know our slope. That's the m value, right? So now that you know what your slope is, now go ahead and figure out what is the actual equation of the tangent line from there. Now, know for most people, when we go and do this, we start by setting it up as y equals mx plus b. That's not the only way to do it, of course. You could also use like point slope form or something like that. But I can go ahead and plug in my y coordinate. So that's going to be the pi plus 3. And then equals m. So that's going to be my 3 minus 3 root 3 times x. So that's going to be times pi over 3 plus b. That look a little bit weird and ugly? Yeah, kind of. I mean, that's a kind of an awkward way for it to look, right? We got the root 3's in there, we got some pi's in there, but we can still do it. So just trust your methods and work through it from there. First thing I would do is I distribute the pi over 3 here into those parentheses. So I'm leaving this as a pi plus 3 on the left side, and then 3 times pi over 3 would just be pi, minus 3 root 3 times pi over 3. Well, the 3 here and the 3 here are going to cancel each other out, so that actually ends up giving me pi root 3 plus b. And now we can move everything over to the other side. Now notice that means I'm going to subtract the pi here, and I'm going to subtract the pi here. So those are just going to cancel each other out. So the pi's totally cancel. So really, all I'm going to end up having to do is worry about the fact that I'm going to be adding this pi root 3 to both sides. Now, the pi root 3, of course, is not a like term with the 3. So after we work that through, we're just going to end up with 3 plus pi root 3 equals b. But now that we've done that, we have our y-intercept. So the last step now is just to write the final equation of the tangent line. All right, so then to get our final equation then, we're going to go y equals m, so that's my slope. So this is going to be the 3 minus 3 root 3 x plus b. So plus the 3 pi, oops, I forgot the plus in there, 3 plus pi root 3. Does that look like the typical kind of linear equation that we've worked with in the past? Not so much, but that's okay. I mean, if you really wanted to make it look like something much more typical to what you're used to, you can calculate 3 minus 3 root 3, right? You can get that as a decimal, and you could also do the same thing with the 3 plus pi root 3. You could get that as a decimal, and then it would look much more similar to what you're used to seeing. It is the same thing, just we're leaving it in an exact form here because we can, and it's a little bit more tidy that way. All right, so for this problem, we're looking for where the graph has a horizontal tangent. So once again, we're looking at a tangent line, right? So if I'm going to be finding the tangent line and dealing with its slope, of course that means finding the derivative. All right, so yeah, finding the derivative of this one is going to require a product rule because we really have e to the x times the cosine of x. So f prime of x here will equal original times derivative. Derivative of cosine is going to be negative sine, plus derivative, so the derivative of e to the x is e to the x, it's its own derivative, times original cosine of x. So now if I want to know where the tangent line is horizontal, because this is the equation for the tangent line, I'm going to set that whole thing equal to 0. All right, so, and when I'm setting it equal 0, I just want to make my life a little bit easier, so I'm going to clean that up a little bit. I'm going to write this as e to the x cosine of x minus e to the x sine of x, just because that's going to be a little bit easier to look at there. All right, now we need to solve it. Now, one strategy for going about solving this, and there's a few different ways you could do it, even just kind of logicking your way through it, but one great way to do this is actually something you learned back when you were solving quadratics. And one of the techniques for solving a quadratic was solving it by factoring, because we could use the zero product property. We could use the fact that 0 times anything is 0. And you'll notice there is some factorization we could do with this one, because I could factor that e to the x out of both terms. So I could write it as e to the power of x times cosine of x minus sine of x. Well, remember what we did back when we did quadratics like that. We could then say, well, if I can make the e to the x equal 0, then of course the whole thing will equal 0, because 0 times anything is 0. Or I could set this cosine of x minus sine of x also equal to 0. If I can make that equal 0, then again, 0 times anything will give us 0. So as we take a look at like that first one, e to the x equals 0. E to the power of what equals 0? I heard 1. E to the power of 1 equals e, not 0. What about then e to the 0? What does e to the 0 equal? 1. Yeah. So it's not either of those, and it's not 1 or 0. Think back to what the graph of e to the x looks like. Can you still visualize the graph of e to the x? I hope so. Let's take a quick look at it here. It's an exponential function, and all of our exponentials look the same. It's just a matter of how quickly they're increasing. So notice then, we have an asymptote in it, right? A horizontal asymptote. And where is that horizontal asymptote? At 0. In other words, if it has that asymptote at 0, that means it's approaching 0 but never actually reaching 0. Therefore, e to the x equals 0 has no solution. So there is no solution that's going to come from the e to the x equals 0 part of this equation. Instead, we look over here for a solution. And I'll tell you here, yes, there is a solution to this. Right now, if I'm going to make cosine minus sine equals 0, basically that means that they have to be equal to each other, right? Or you could even actually modify the equation to look like that. You could add sine to both sides. So we could know that we need cosine to equal sine. So basically this is a unit circle problem now, where on the unit circle, at what x values does the cosine value equal the sine value? Yeah, pi over 4. So pi over 4 is a solution to this problem. Is it the only solution? No. Yeah, 5 pi over 4 is another one. All right, so 5 pi over 4 and pi over 4. Great, is that all of them? Well, not really. Because remember, this is a circle, right? And we just figured out this one up here at pi over 4. And we just figured out this one down at 5 pi over 4. But of course, after I get here, I can keep going around. And I'll hit this one again. And I'll hit this one again. And I'll hit this one again. And I'll keep being able to go around and around and around this circle an infinite number of times, right? Which means there's an infinite number of solutions. I'm not about to try to write them all out, right? So rather than writing something that looks like this, we can instead say that x equals what? How would I write that? Yep. Notice that pi over 4 and 5 pi over 4, they're exactly straight across from each other, so we don't need to do two separate ones. We can just do pi over 4 plus pi gets me to 5 pi over 4, plus another pi would bring me around to the 9 pi over 4, which is getting back to our pi over 4 there. And so we do pi k, where k is just an integer value there. And so then this would actually be the solution to that problem. Now, doing this one, of course, you need your unit circle really well, right? Now, as we start getting to that point, I know some of you going and looking it up, which is a fine thing to do, but we need to get to the point where we don't need to. You really do need to have this down, because in your brain, you should have a picture of these values so that you can quickly find out that that's where they were the same, and you would know exactly what they are. We really do need to know this whole picture, everything involved in this, the sine values, the cosine values, the radian angles, and the degree angles. Although the radians are going to be the most important going forward for sure, but we don't want to lose the degrees as we go. And got to know all of these different values. And because if you know these, I only have sine and cosine up there. I didn't write up the tangents, because of course if you know sine and cosine, you can find tangent, because tangent is just sine over cosine. And you could also then find cotangent, or you could find secant, or you could find cosecant, just from the sine and cosine values. So that's why this is so important. So many of those other things are hanging on these pieces of information. All right, we're going to do one last problem here together today, and that's going to be this one. I'd like you to find the second derivative of this function. Now, hopefully you recognize at the start of this one that this is the same problem that we were just working with in the last one, where we're solving for the horizontal tangent line. So we'd already found the derivative, and in that problem, we wrote the derivative in a couple different ways. We at first cleaned it up into that, and then because we were trying to find the horizontal tangent line and solving it equal to 0, we put it into that factored form. So as I'm thinking back to that first problem, since I have both of those, I'm looking at them and deciding which one do I think is easier to work with. And this is really a personal choice here. You could go either way. But for me, when I look at it, I see that if I'm going to find the derivative of this first one, that I'm going to be doing product rule and product rule. So I'm going to have to use product rule twice there if I do it that way. If I do it with the second one, I'm going to be doing product rule, where those are the two parts that I'm multiplying. I'm only having to use product rule once for doing that second one, so for me at least, I like doing it from the second form. So that's the one that I'm going to go from. Whichever way you do it though, you will get the same answer. So then, we're going to go f double prime of x now, equals. So we're going to go original times derivative. So original, of course, e to the x, and then times the derivative. So derivative of cosine is negative sine, minus the derivative of sine, which is cosine. All right, so that's original times derivative plus derivative of e to the x is just e to the x, times original. And so we leave the cosine minus sine as it is this time. Please note the parentheses that I'm including. I've seen a few of you who have a tendency to drop your parentheses, and it's causing you some headaches, causing you some problems. Be diligent about the parentheses. They change what all these things equal quite a bit, right? All right, from here we're going to simplify, and there's a few different techniques you might use to simplify. For me, I'm going to use what I think is the most common one, where I'm just going to multiply those e to the x's in. So that's going to give me negative e to the x sine of x, and so on. And so now that I've gone ahead and distributed in all my e to the x's, it's a little bit easier to see where I have some like terms, because I have a negative e to the x sine of x and a negative e to the x sine of x there. And I have a negative e to the x cosine and a positive e to the x cosine here. Notice that e to the x cosines are going to cancel each other out, because one of them is negative and one of them is positive. However, the sines will not cancel each other out, because both of those are a negative e to the x sine of x. So that's going to end up combining to give me negative 2 e to the x sine of x. That then is done. This is one of the few problems that we've seen so far, at least, where our first derivative looked more complicated than our second derivative. Oftentimes they can actually get to be bigger types of functions, especially when you have to use product rule and product rule. But as you can see, sometimes it will actually kind of simplify itself as you go.